Now let's talk about how this cache memory is implemented, at least logically. So what happened is, first of all, we assume this block size k and number of cache line in the cache is a power of 2. Why we assume it? Because you remember, like, to compute the cache index and tag and block address, even for block address from the given address A, they are division and modulus operation involved. And as we know, this we started already the divider circuit, right? Integer division circuit, which is very slow, right? Which is like, it's more, it needs 32 step for a 32-bit operation, which means it is like many cycles actually involved in completing a division operations where we can compute the mod and div quantities. Now, if we need to deploy the division circuit along with this stack access mechanism, it will be much more slower, and our like final target of giving a faster memory to the processor will be gone. Like, because division is a really slow circuit. So, but what we realize that if the k and c, this number of words in a block and number of cache line, are in order of power of 2, like if it is like, let's say, 256 word or 512 word per block, and there are cache line like 1024 or 2048, which are perfect power of 2, we don't need a div and mod operation. How? Let's take this 26-bit address. Okay, we can just make it 32-bit as well, it doesn't matter. So here, what we are defining, my block size is 256 word, and there are 1024 cache line, indexes 0 to 1023. Now, 256 word, which is 2 to the power 8, that means to make a block address from a given address, which is, remember, it is B, block address is A div K. So A bit is given, this is 26 bit, and K is given, which is like power of 2 to the power 8. Now, what is my div operation? If I am actually computing a quotient, dividing some integer with the power of 2, like 2 to the power 8, what we all need to do, take, like, ignore the first 8 bit of the bit pattern on the LSB side, and rest of the 18 bit on the MSB side is my quotient value, and the first LSB 8 bit is my remainder for a integer division with a divisor that has a value of power of 2. Okay, so remember, like, it's more like, if you recall, your multiplication with the power of 2 value of any integer is practically left shift that many bit. Okay, let's say you are multiplying something with 16. Okay, that means 16 is 2 to the power 4, so that means you need to shift the whole bit pattern towards the left as 4 bit for getting the answer of multiplication. Similarly, for the division, if given a bit pattern, okay, and you are, let's say, dividing them like with 16, with that value representing that bit pattern, what you need to do, right shift this bit pattern 4 times, because 2 to the power 4 is 16, and whatever bit pattern you get is your quotient value. And that 4-bit pattern that left out as a shift operation, those 4-bit pattern determines your remainder. So we are taking advantage of that fact. So given an address 26-bit, and we know my block size is a power of 2, which is 2 to the power 8. So my block address is the MSB side 18-bit out of this 26-bit. So that other LSB side 8-bit become my remainder. So that's what my block address. So block address is from bit 8 to 25. And now we are doing the div operation to determine the tag and mod operation to determine the cache line index. So div operation, so again your cache line index is like 1024, which is 2 to the power 10. So you need to, for modulus operation, what you need to do, you need to pick up the 10 bits of the LSB side of the block address, and that's your index. And rest 8-bit become your div operation result, and which is a tag by definition. So this 8-bit bit from 18 to 25 with that respect become my tag, which I can need to compare with the tag stored in that cache line. So you see, with this assumption, both my number of cache line and number of words in a block or block size, if it is a power of 2, we don't need a division circuit at all to involve. What all we need to do, count the bit and use those corresponding set of bits as like in block index, which is the first 8-bit. In this case, it's a index at within which the corresponding data has to be retrieved, and then my block address become the rest of the bits, and out of that we chop up, and 10-bit become my line index, cache line index, and rest of the 8-bit becomes my tag. So what we do from this memory, this is a direct access memory, we access that corresponding line. In this example, let's say it is a 3 index line, cache index line 3. We access them and we retrieve the tag, and we make an equality circuit, which is nothing but XOR. Like if XOR result 8-bit XOR between the tag stored and the tag evaluated are 0, then it's a match. Otherwise, it's not a match. Then this match goes with the AND from the valid bit. How do we know if this line is not empty, like as a power of operation? So we must make an AND with the valid bit, and that output is my hit. So this is how the hit signal is generated, and controller basically goes and recognize this hit. Like in this case, it is memory controller, by the way. It's not the controller as we know so far inside the processor. It's a memory controller. And if the memory controller sees it's a hit, so what it does, it accesses that corresponding line, so which is like k number of blocks, k number of words, 256 word, and then between that 256 word, the corresponding block index, which is the first 8-bit of the address, given address, that index is accessed within this block. So this access is 2, so it is accessing the third word within the block and giving it back to the processor. So this is a simple circuit in a sense that we avoided division circuit to compute mod and div because of the property of how we integer divide with a value which is power of 2. So that's one limitation is posed to the cache architect, that they need to make sure your block size and number of cache line has to be a value which is power of 2. So that's all for this lecture 20. If you have question, please send me an email or update into the Canvas discussion or ask me in class.